Okay, this is question number 1 from the electrostatics review packet. The question reads, the figure shows 2 point charges, each of charge negative 2q, and third point charge negative q is placed on the x-axis at x equals 2a. So we've got a sketch of the situation up here, and the first question that we're asked to do is to derive an expression for the magnitude of the net force on the charge q due to the other 2 charges, and they want to know additionally its direction. So there's a couple of things to recognize here. First of all, so we're focusing here on this charge, which is negative q, and we want to know the force acting on it. For starters, we're going to recognize that these are 2 point charges, negative 2q, and that the magnitude of those charges can be found using Coulomb's law. So as soon as you see the concept of net force and electrostatics, you should be thinking Coulomb's law, which means that the equation for the electrostatic force being the constant k times the magnitude of the 2 charges, q1 and q2, over the distance squared, in this case I'll use the variable r, is going to come into play. As we look at our sketch, we should recognize that there's a right triangle here. So we've got 2 known sides, that's a, and then of course the base of that right triangle is 2a. And we are interested in this distance that I've drawn here in green. So we're going to develop an expression. Let's start off with defining that, that length r. We should recognize that this is a right triangle, and I can use Pythagorean Theorem. So r squared is going to be equal to the sum of a squared, and in this case 2a squared. And so therefore I can say that r, which is the important dimension, is going to be equal to the square root of a squared plus 2a squared. In this case, 2a squared becomes 4 times a squared. And so I get a squared plus 4 times a squared, or, of course, 5, square root of 5 times a squared. Finally, what I'll do is I'll divide that into, I'll separate that into the square root of 5 times the square root of a squared. And so finally, my expression for that distance r is going to be root 5 times a. All right, so this piece is going to come into play here as I define the distance between the point charges. Let's go ahead and continue. So the next part of developing that expression is going to be to say, all right, well, let's go ahead and just for sport here, I'm actually going to erase that right triangle that I make. Now let's focus on the forces. Let's recognize that the y components of the force are always going to cancel out. So there's a force down and to the right that can be resolved into x and y components. So there's a downwards y component of that force, and there's a rightwards x component of that force. I'll go ahead and define those there. And likewise, I could say that due to the charge over here, the negative Q2 charge, there's a force acting up and to the right, which again can be divided or resolved into its x and y components. So I have a positive y component and then now another duplicate x component along the x-axis, both rightward pieces. You should immediately see here that the 2 y components are always going to cancel out, and ultimately I'm going to be left with a net force that is simply the sum of the 2 x components. So what I can say then is that my expression for the net force acting on the single charge minus q is going to be equal to 2 times k, which is the constant, times q1, which in this case I'll just define as one of these guys, negative 2q. And I'm just going to use 2q, the magnitude. And the reason I'm not worried about this sign here is because I've already taken care of its direction. We know it's going to be a repelling force because they both share the same charge. So I'm going to get k times 2q times q, which is the magnitude of the charge of interest here, over r squared. Now, in this case, r squared can be defined as root 5a. So I'm going to write that as root 5 times a, and I need to remember to square that whole thing. But I just want the x component of that. So normally I would just feel comfortable saying, all right, let's just call that cosine theta and be done with it. However, they've specifically asked for me to define this in terms of the fundamental terms QA and other fundamental constants, and I can't use cosine and theta because they're outside of that. So let's express cosine theta in terms of those, in terms of QA, Q and A. In this case, cosine is defined as the adjacent over the hypotenuse. I'm thinking SOHCAHTOA here, the adjacent side of this right triangle of interest. By the way, let's take a look at that. Here's the right triangle of interest, the adjacent side here, and this is going to be the hypotenuse. Actually, let's do this. Let's go ahead and define the adjacent side as 2a, and let's define the hypotenuse as r, which then can be substituted here with the expression root 5a. So I get 2a over root 5a, and so therefore the cosine of theta can be expressed as 2 over root 5, which is going to do a whole lot better because of that requirement right there. So instead of writing cosine theta in order to reduce this expression into just the x component, I'm going to multiply that by the basically 2 over root 5. All right, so it's a little bit ugly at first, but let's not freak out. The first thing I'm going to do is take care of multiplying all of these things together and combining some terms. So let's go ahead and do that. I'm going to multiply that 2, and that 2. So 2 times 2 is 4, 4 times 2 is 8. I get 8 times k. The k doesn't go anywhere. Times q is q squared. And then in the denominator, I've got root 5 times root 5, well, root 5a times root 5a. So that's going to give me 5a squared, and I can't forget that root 5, which stays down here in the denominator. And so, however you want to write that, let's go ahead and finish it as 8 times k q squared over 5 root 5a squared. And so that becomes an expression for the force, the net force acting on that charge q. The next question asks us to derive an expression for the magnitude of the net electric field at the origin due to the other three charges. Oops. So at the origin, the electric field due to the two negative 2 charges is going to cancel out. Remember that the electric field is a vector. Think electric force, and then the force, of course, the electric field is going to be the force per unit charge. So if the force is 0 at the origin due to this guy and this guy, then they actually don't matter. They don't contribute to the net electric field. They cancel each other out. So the only electric field is going to be due to this guy over here, negative q. So if I were to put a positive test charge at the origin, that would be pulling that test charge to the right. So we know that the electric field and the electric force will be rightwards at the origin, and it will only be due to the contributions of the negative q charge at position 2a. So by definition, the electric field due to a point charge is going to be equal to kq, where q is the point charge, over r squared. All I need to do is substitute in that expression in for r, which is, in this case, root 5a. I'm sorry, not root 5a. That was this length. In this case, it's just 2a, which is the distance away that the point charge is from the origin. So that becomes kq over 2a, but I got to remember to square that. So then the expression for the electric field becomes kq over 4 times a squared. And of course, I need to indicate a direction, in this case to the right, since it is a vector. By definition, electric potential is going to be equal to the sum of the contributions of all of the point charges. Remember that the electric potential is a scalar, so it's going to be sigma kq over r. Again, this is on your equation sheet. So, there are a lot of different ways to write this, but what I would do is I would say k times q1 over r plus q2 over r plus q3 over r. In this case, I have 3 charges that are contributing. The first one has a magnitude, so it's going to be k times negative 2q over our R, in this case, is just going to be A. And I'm going to add to that the second one, which is just below it. So I got the 2Q on charge. That's not an A, sorry, that's a Q. So I get negative 2Q over A, and then finally the last one is negative Q over 2A. All right, so now I've got this interesting thing that I'm going to deal with here. I need to kind of combine some like terms. So I'm going to go ahead and do that in red right underneath it. I'm going to call the common denominator 2A, which makes that negative 4Q on the top. I'm going to add to that the same thing. This is 2A on the bottom. That becomes negative 4Q. And now I've combined my terms with a least common denominator. I can combine the terms. So my denominator is 2A, and I've got negative 4Q, and Q, which is going to give me negative 9Q over 2A as the total potential there at the origin due to the 3-point charges. Oh, don't forget the constant K here. I left that out of the numerator, and it should be there. All right, let's take a look at this last question. It says on the axis below, sketch a graph of force on the negative Q charge caused by the other two charges. If I were to basically drag the negative Q charge, and I'm going to get rid of this stuff here. If I were to drag the negative Q charge along the x-axis. So as I look at the sketch here at the top of the page, yeah, that's behaving badly. Okay, so where are we? We're right here. So basically what's happening is taking this negative Q and moving it horizontally this way. Let's recognize that when I'm right here at the origin, when I'm right at the origin, the net force is going to be equal to 0. When I move rightwards along the positive y-axis, let's say I'm right here, the y components cancel out and the net force is rightwards. And that x component grows until I get to about 45 degrees, and then as I get further away, due to the distance and the fact that this is now less than 45 degrees, well, it's a function of the distance away, that x component is going to get smaller. And the mirror image happens here on the other side as well. So right when I'm at the origin, the net force is 0, everything's canceling out, and then let's do this in a different color. As I go to the left, I get a large net force, which is maximum at about 45 degrees, roughly a distance of about A away. And then as I get further and further away due to that distance, the magnitude of that leftwards force gets smaller and smaller with respect to that distance away from the origin. So if we're to graph that, we're going to get something that looks like this. Let's go ahead and pan back down on the page and sketch that in on the axis. So when I do that, I'm going to get something that looks like this. We definitely know that we're going to be at 0 here. We're going to have a maximum positive, roughly about a distance A away. And then it's going to come back down and approach 0, obviously never getting there because the electrostatic force acts at great distances. The distance asymptotically approaches 0. And then here we have the same thing happening in the negative direction.